Good afternoon. Today we're going to be talking about section 4.9, antiderivatives. So if we can perform differentiation, can we undo what we've done? As in, can we work backwards from what we just did? And the answer is yes. The goal of differentiation is to find a derivative f prime of a given function f. We can also perform the reverse operation, that is, given a function f, we can find the antiderivative, capital F, such that capital F prime equals f. A function capital F is an antiderivative of lowercase f on an interval I, provided capital F prime of x equals lowercase f of x for all x in I. So how exactly do we do that? And we do that through thinking backwards. So consider the derivative formula d dx of x equals 1. It implies that the antiderivative of f of x equals 1 is capital F of x equals x, because capital F of x prime of f of x equals lowercase f of x. Using the same logic, we can write d dx of x squared equals 2x, the antiderivative of f of x equals 2x, is capital F of x, x squared. So that brings the question, does a function have more than one antiderivative? And the answer is yes. Consider that first example we did where lowercase f of x equals 1. Our antiderivative could be x, or it could be x plus some number c, where c is some real valued constant. In either case, when we take the derivative of capital F, we get f of x. So what does this mean? Let capital F be any antiderivative of lowercase f on an interval I. Then all the antiderivatives of capital F on I have the form capital F plus c, where c is an arbitrary constant. And I don't think I included this, but it'll look something like this. If I have that guy, or I've got that guy, or I've got that guy, pretend these are parallel lines, all of them have the exact same slope as one another. That is, all of them have the same tangent line. That is, all of them have the same derivative. But you can see that there are three different functions. So capital F plus c captures all of these, and it's the family of antiderivatives. So using what we know about derivatives, let's find all the antiderivatives of the following function, f of x equals 3x squared. We know that the antiderivative of f of x are x cubed, or is x cubed, so to find all of them, we just add plus c. And how do I know that? Well, if I say d dx of x cubed, I get 3x squared, which is my original function. And the family just means I can say d dx of x cubed plus c equals 3x squared. So using what we know about derivatives, use what you know about derivatives to find all the antiderivatives of the following function. And this one might seem tricky, but we just have to remember inverse trig and trig derivatives, specifically inverse tangent. So this one is a little bit more challenging, but remember that d dx of tangent inverse is 1 over 1 plus x squared. So the antiderivatives of lowercase f of x are capital F of x equals inverse tangent of x plus c. This plus c is very, very important, and yes, you will get points off if we ask you to find the family of antiderivatives and you forget a plus c. And yes, you will get points off if this happens in Calculus 2, Calculus 3, engineering classes, physics classes. Plus c is very, very important. Use what you know about derivatives to find all the antiderivatives of the following function, f of t equals sine of t. So this one might be a little bit easier, but it's still a little bit tricky. Recall that d dt of cosine of t is negative sine of t, but we seek a function whose derivative is sine of t, not negative sine of t. Observe that d dt of negative cosine of t is sine of t. It follows that the antiderivatives of f of t are negative cosine of t plus c. Plus c, plus c, plus c, plus c. If it seems like I'm harping on this, it's because it's very, very important. So now let's talk about notation. We use the notation d dx f of x to mean take the derivative of f of x with respect to x. So there's got to be a notation for find the antiderivative of a function f of x with respect to x. And indeed, it's this little stretched out s looking guy. And it's called an indefinite integral sign. Every time an indefinite integral sign, this little squirrely s, appears, it's followed by a function called the integrand. So that's my f of x is the integrand. And then by the differential dx. The integral sign tells you to take an antiderivative, while the integrand, that f of x, tells you what you're taking the antiderivative of. And the differential tells you with respect to which variable. So I could easily write something x plus y. And if I didn't include dx or dy, you wouldn't know which one to take your integral with respect to. So you always need to include dx or dy or dt or whatever is important. So here's an example of the notation. The integral of 3x squared dx is x cubed plus c. So let's talk about the power rule. For p not equal to -1, we have the integral of x to the p dx equals x to the p plus 1 divided by p plus 1, quantity plus c. So I'm going to show a quick example of this. So if I say the integral of x squared dx, in fact, let's use a function we've seen before, 3x squared dx. My x squared becomes x cubed. My 3 stays put, and then I get p, which is 2, plus 3 in my denominator. So my 3's cancel out, plus c, which is equal to x cubed plus c, which we've already seen before. And this actually ties into the next rule that we have, which is the constant multiple rule. The integral of c times f of x dx is the same as the c times the integral of f of x dx. So that is to say that the integral of 3x squared dx is the same as 3 integral x squared dx. That's just what that's saying. You can always pull your constant multiple out. Then we have the sum rule. If we have f of x plus g of x within our integrand, we can split it up. So the integral of f of x plus g of x dx is the same as the integral of f of x dx plus the integral of g of x dx. So in this one, determine the following indefinite integral. And this one's kind of meaty to start with, which I don't know why your textbook likes to do this. It likes to give you really hard examples for really simple concepts, but you'll see that again in Calc 2. So let's go through this example. My first step, which occurs right here, is I FOIL everything out and I go from z squared plus 1 times 2z minus 5 to 2z cubed minus 5z squared plus 2z minus 5. I can split these up using the sum rule because it's a sum and difference rule, and I get the integral of 2z cubed dz minus the integral of 5z squared dz plus the integral of 2z dz minus the integral of 5 dz. Then I use my constant multiple rule to pull out any constants, so I get 2 integral of z cubed dz minus 5 integral of z squared dz plus 2 integral z dz minus integral 5 dz. Then I just perform using my power rule, and I make sure to keep everything going. So my final answer is 1/2 z to the 4th minus 5/3 z cubed plus z squared minus 5z plus c. And we can check our answer by differentiation. If I differentiate this bad boy, I better get this bad boy back. So here are some indefinite integrals of trigonometric functions. The integral of cosine x dx is sine x plus c. The integral of sine x dx is negative cosine x plus c. The integral of secant squared x dx is tangent x plus c. The integral of cosecant squared dx is negative cotangent x plus c. The integral of secant x tangent x dx is secant x plus c. And the integral of cosecant x cotangent x dx is negative cosecant x plus c. And these, there's no rhyme or reason. You just have to remember that this is what's going on. So now determine the following indefinite integral. Let me check something real quick. Yes. So this one, we get to use 2 pi integral sine x dx minus 2 cosecant squared x dx. So that should help push you in the right direction, and then it's just a matter of applying those trig rules. The solution, which you can check for yourself, is 2 cotangent x minus 2 pi cosine x plus c. So these are not trigonometric functions, so ignore that. These are just different functions. Now, much like how the derivative of e to the x is e to the x, the integral of e to the x is e to the x plus c. The integral of 1 over x is actually the natural log of the absolute value of x plus c. And then we've got a few more for inverse trigonometric functions. So the integral of dx over square root of 1 minus x squared is inverse sine x plus c. The integral of 1 over 1 plus x squared dx is inverse tangent x plus c. And the integral of 1 over x times square root x squared minus 1 is secant inverse absolute value of x plus c. So determine the following integral. Here's a quick little hint. And that's just by saying we can divide each element of our numerator by the denominator separately and then add those together. So that should help you out really quick. The solution begins with simplification, just like I showed, and I already skipped ahead to this step. So my final solution is 2/3 x squared plus the natural log of x, quantity plus c, plus c plus c plus c plus c. And that's it for me today. Just remember, always add a plus c.